Good morning, everybody. Today we've got a Codeforces round. There's a new change in scenery because I am here in Wisconsin, but this is educational round 111, so it's a palindromic round, and it should be fun. Let's jump into it. I'm on a new computer here too, so it's going to be a little bit different than normal, but that'll be fine. All right, find the array. Let's call an array A of n positive integers beautiful if the following condition is held for every integer from 1 to n. Either a at I equals 1, or at least one of the numbers a at I minus 1 or a at I minus 2 exists in the array as well. So if you remove duplicates, if every jump in the array is of 1 or 2. Right? So this is, oh wait, what are we printing? So print t integers. The ith integer should be the minimum possible size of a beautiful array with sum of elements equal to s. I see. Is it always possible? So your sum of elements, what's the biggest you can get? So you can have, let's go to Codeforces here. Sorry, this text is absolutely tiny. I'll make it bigger in just a second. Yeah, so so you can get a sum of 1. What if you want a sum of 2? 2 is not possible, right? Because you need either to add a 3 or a 2 as the second digit. So your sum can't ever be 2. Oh, but you can have multiple ones. Okay, gotcha. So you can have 1, 1. That's allowed. All right. So this is a legal array if you have 1, 1. So anything is possible because you could just have all ones. All right. So now what's the question? What's the minimum possible size of a beautiful array with sum of elements equal to s? All right. Yeah, so if we use the biggest number we can each time, then that will be sufficient, right? Because then whatever the remainder is, we can place that when we need it. So that should be fine. Let's implement that. Yeah, runtime should be fine as well. So int s equals this, and then int count equals 0, and then place equals 1. So while s is greater than 0, then s minus equals place, capital S for some reason, and then count plus plus. And then place plus equals 2. This out, count. All right, I think we should be good there. Let's submit this. Oh, you know what we don't have? Because I haven't set it up yet, we don't have CF notifications. It's gonna be a mess. All right, anyway, on to problem B. Looks like we got it. Nice. Did we get it? Yeah, we got it. Nice, nice. All right, cool, cool. All right, problem B, min cost deletion. You're given a string s of length n consisting only of characters 0 and 1. You perform the following operation until the string becomes empty. Choose some consecutive and equal characters, erase it from the string, and glue the remaining parts together. Any of them can become equal. Okay. So we can erase string 111, gotcha. All right, so it doesn't have to be maximal. When we delete a substring of length L, we get A times L plus B points. Your task is to calculate, can A and B be negative? They can. The maximum number of points that you can score in total if you have to make the string empty. So in total, we're gonna need A times n. That's the contribution of A. So it's just how many times does B contribute. And either it's, well, you can delete all the ones or all the zeros and then one more. Or you can delete every continuous segment, but you might as well just delete every one and then every zero. So B, it's either all ones plus one or all zeros plus one. Yeah, or you delete every character individually if B is positive. Okay, so let's implement that then. It's multi-test case, okay. Oops. Int n equals this, A equals this, and then B equals this. N's always small, right? So we don't have to worry about overflow. So int ants will be n times A. And then if B is greater than 0, we do one thing, otherwise we do something else. So if B is greater than or 0, ants plus equals n times B. Otherwise, we want to minimize the number of sections. So int count equals 0, I guess, or we want int z count equals 0, and then 1 count equals 0. This is after we've removed duplicates, so it's not actually the total number of zeros and total number of ones. Yeah. So then for int I equals 0, well, I guess we also want the last. So char last equals, oh, we need to read the thing, read the string. So char array string, yeah, string equals, let me fix something real quick. I just got an idea. We can do this. I think. Look at that. Boom. All right, now my camera's not gonna run out of battery. What a pro. Maybe, I don't know, who knows, or maybe not, we'll see. Camera's dead. There we go, I think we're back, okay. All right, awesome. Okay, where was I? Yeah. So this equals fs.next.toCharArray. All right, and then last will be equal to, I don't know, the character A. Now for char C in string. So if C equals last, then continue. Otherwise, last equals C, and then if C equals 0, then z count plus plus, else 1 count plus plus. All right. So finally, ants plus equals math.min of 1 plus z count, or 1 plus 1 count, times b. Then we print the answer. And we should be good. All right, let's run samples for this because it's a bit messy. 615 minus 2 looks good. All right, submit that. Awesome. Got that as well. Nice, nice. All right. Problem C, Manhattan subarrays. You've got 2 points, P and Q. You can look at the Manhattan distance between them. Let's say 3 points, P, Q, R, form a bad triple if the distance between P and R is the distance between P and Q plus the distance between Q and R. Okay. That makes sense. Let's say an array is good if it's impossible to choose 3 distinct indices such that points Pi let's say an array is good if it's impossible to choose 3 distinct indices, such that bi, so if you make the x's the places in the array, and then the y's the indices, then that's a bad triple. So what makes something a bad triple? If you sort the things by x, then the y's need to be sorted either in increasing or decreasing order, right? If you do a v, if you go down and then up, then that's not, yeah. So they need to be like in a line, right? They either need to be increasing x, decreasing y, or vice versa. All right, you're given an array. Calculate the number of good subarrays of A. Gotcha. So a good subarray has, can a good subarray ever have 4 elements in it? You can't have an increasing subsequence of length 3. You can't have a decreasing of length 3. It's got to be increasing, decreasing. So like, let's say it goes up. You go here. You can have it of length 4. Okay. What about 5? I don't think you can have anything of length 5. Yeah. So things of length 3 are, yeah, any any like mountain, I guess. So I guess let's look at the things. Anything of length 2 is good. Yeah. So anything of length 2 is good. So the question is how many things of length 3 are bad? And then how many things of length 4 are bad? The things of length 3 that are bad are easy to count. It's how many increasing and decreasing. So for each middle element, we look at how many things before less than or equal, how many things after less than or equal. So we can do that with a, how big are the numbers? I guess we can do it with a segment tree if we needed to. Yeah, so we can use a segment tree or a compressed bit. I guess we can always coordinate compress, right? So we can use a bit. So let's use a bit for that. So that would handle the 3 length. Now the question is, what about the things that are 4 long? So we can have an increasing subsequence, and then we can have another increasing subsequence. What constraints do we have? So this has to be a decrease, and this has to be less than that. Okay. Yeah, you've got to go like up and then down. It's tricky. It's got to be something kind of like this. So of length 4, you've got to go up, down, and then up, but this 4th element has to be between these two. Oh, so I guess you just have these two things, and then everything needs, like, both of these need to be between these two. Yeah, that makes sense. So you have 2 elements that are like the boundaries, and then you need to pick the first and last between those 2. That sounds like it would be n squared to calculate though. So how do we do it faster? Oh wait, what is a subarray? Oh, it's a continuous thing. Gotcha. Yeah. So, okay. So this is easy. So since it's continuous, we can just try every pair, right? We know the length is at most 4, so we just try every pair. Yeah. Really easy. Okay. I thought it was I was thinking subsequence, I guess. In which case it's a bit harder, but still possible. I think you can still do it. Okay, sounds good. So nice and easy. Int n equals this. Int array a, read array of size n. And then we'll say, well, I guess have a long count equals 0. This out the count at the end. Then for int l equals 0, l is less than n, l plus plus. For int r equals 0, r is less than, or r equals l. So if r is greater than l plus 4, well, I guess let's just say if r minus l plus 1, that's the length. If this is greater than or equal to 5, then break. If r minus l plus 1 is less than or equal to 2, then count plus plus and continue. Otherwise, it's 3 or 4. So we might as well make this array. So a at I will be, oh, this isn't a. We'll call this b, I guess. B at I is a at I plus l. Okay. So then for int I equals 0, I is less than b dot length, I plus plus. For int j equals I plus 1, j is less than b dot length, j plus plus. For int k equals j plus 1, k is less than b dot length, k plus plus. Then if b at I is less than b at j, and b at j less than b at k, then continue outer. We'll call this outer. Or, I guess we'll just do this twice. So, or it's in the reverse order. Continue outer. Otherwise, count plus plus, and then print count at the end. Looks good. All right, let's run that. Okay, we're crashing. This is less than b dot length. 10, 14, 3. Oh, we're getting this wrong. Okay. Yeah, these less thans should be less than or equal to. And then we should be good there. Looks good. All right, nice and easy problem. As long as you read it correctly, you know. The subsequence one is also a good problem. I mean, it's a bit harder, of course, but yeah, there you go. All right. Well, I guess we should. Did we get it? Yeah, we got it. Nice. Problem D: excellent arrays. Let's call an integer array a1 through an good if a at I is not equal to I for each I. So let's call it good if it's what is this? This is a derangement, I think, derangement. Let f at a be the number of pairs, ij, such that the sum of the elements is equal to the sum of the indices. Okay, gotcha. Let's say an array is excellent if it's good, if is L and R, yeah, okay. So if each element is in some range, And if f, what is f? Oh, the number of pairs that match up is as maximum possible among all good arrays of size n. Okay. I see. The first and only line of each test case contains 3 integers. And then print the number of them. Okay. Gotcha. So you have n, you have a bound on the numbers, and then you want to print how many ways there are to make an excellent subarray. Oh my goodness, for real? Good morning. What if we do this instead? This is kind of annoying. Okay. Technical difficulties, everybody. Sorry for the terrible no. That's kind of annoying, isn't it? A little bit annoying. There we go. Okay. Well, we're gonna cross our fingers and hope that that winds up being okay. Yeah. All right. I'm back. Okay. All right. So I'll have to keep an eye on this now, I guess, because it's being annoying. Yeah, so what's the idea for this problem? We need, I guess, first of all, how many problems are there? There are D, E, and F. We have 3 more. Okay. It's going to be a tricky set. So let's think for a minute. We need to have the same like decrease from the, yeah, so if this is like position 2 and this is position 4, let's ignore, or like let's include the value of 2 in the value of that position. So in this case, right, if this is a 3, we'll consider it as a 1. And if this is a 4, we'll consider it, and then we put like a 1 here, let's consider it as a -3. So for something to be excellent, then we need for a pair to be good, it needs to be like 1 and -1, like these need to match. Yeah. So the question is, we need to know what's the maximum number of matching pairs we can get, and then how many ways are there to get that maximum number of matching pairs. Yeah, okay. So how do we do that? So we have an L and an R bound on each position. So for each position, we say this can be like in this range. So we need to add some number here, or we need to add 1 to this entire range, and then find the sum across this entire range. Yeah, so we need range update, and then we need range sum. Right? Range update, range sum. maybe. Okay, so like if we have the range like 3 to 5, that's our range, then in position 1 we can have 2, 3, or 4. In position 2 we can have 1, 2, or 3. Yeah, okay. And then in position 3, we can have 0, 1, or 2. So if everything has to be in this range, the only things that can match are, like, they can't both be too small, right? So the only possible candidates are 3, 4, and 5 could match. Well, that's not true. So nothing can be 0, but everything could match. If you had all 3s. Yeah, so the bigger of the two numbers can be, it could be 3. The bigger of the two numbers could be 3, 4, 5, or 6, 7, or 6, 7. Yeah, that's the bigger of the two, could be any of those. Why is that? Well, the bigger of the two could be anything, right? In general, it has no dependency on the size of this range. Yeah. Okay, how many solves does this have? How are we looking? Some solves? E also has some solves. Maybe you'll read E then. All right, we're given a string S of length n. Each character is either one of the first k lowercase Latin letters or a question mark. We're asked to replace every question mark with one of the first k lowercase Latin letters in such a way that the following value is maximized. Let f of I be the maximum length substring of S, which is entirely the ith Latin letter. A substring is a continuous sequence. Okay. If the ith letter doesn't appear in the string, then fi is equal to 0. So the maximum length substring, so like the maximum run of this letter. Okay. The value of S is the minimum among the values of fi from 1 to k. What is the maximum value the string can have? Oh, okay, gotcha. So, I see. Gotcha, so it's binary searchable. Binary search this value. And then we've got something like, we need a run of length, whatever. K is only up to 17 is sketchy. Why would that be? You could do like a 2 to the n for which things are satisfied, which might be necessary. Yeah, so you could do you can do ADP. What is this naive DP? What does it look like? It's something like, yeah, so we can do DP of mask so we could like binary search DP of the mask and the position, and then transition of K. So this is way too big. 2 to the K. Yeah, so you don't do this. You do mask equals min position. To the K times K transition times binary search. So what's our runtime? So binary search is 17. Times 2 to the 17. How big is this? 17 times 17 times 2 to the 17. Yeah, it should be fine. All right, that was an easy problem to solve, at least. Test case 2. Int n equals this, k equals this. And then we have the array. So k array a, fs dot read array of size n. Oh, sorry. Fs dot next dot to k array. All right, so then we need to binary search this. So int min equals 0, then max equals n. Well, min is not equal to max. Int mid equals min plus max over 2. Static Boolean solve int n. Okay, so this will be, what are we actually binary searching here? This is the required like jump, and then we need a k array a. Okay, so the mid is this, and then if solve required jump, this is just mid, this is a. So if it's possible, that means we can have our answer be bigger. So min equals mid. Otherwise, if it's not possible, then max equals mid minus 1. So in that case, we want a plus 1 here, and then we print min at the end. So what if we're going to solve this? Now what? So we need to know the earliest we can reach each mask. So we'll have int array earliest reachable equals new, oh, we also need k. Yeah. New int array 2 to the k. So then we need to know the next time we can place a run of this many characters. Yeah, so we can do that. So like we need to say like can we place a run at each position? Okay, so let's full screen this. Int array prefix sum for char equals new int array, so we need n. So this is going to be n plus 1, or it'll be k by n plus 1. Okay. So if a at I minus 1 equals c plus a, or a at I minus 1 equals a question mark, then prefix sum for char at c I equals prefix sum for char at c I minus 1 plus 1. Else, oh, I guess we can just do this plus plus. Okay, so now we have the prefix sum for each character. So now we need to say when is the next time we can place each index? So we need int double array next place for index equals new int array. So this will be k by n. Yeah. So now for int I equals n minus 1 greater than or equal to 0 minus minus. I'll go through each char. So I guess we'll make this n plus 1. And then for int I equals 0, I is less than k, I plus plus, next place for index at I n I guess equals n plus 1. So those are all impossible. Okay, so now we need to know if we can place it here. Well, let's just say we can always place it where we do in the next space. So next place for index at I, or at c I equals next place for index at c I plus 1. Okay, let's rename this to c so our indices match. Good. So now if prefix sum for char at this character at I plus required jump minus prefix sum for this character at I, if this is equal to required jump, then next place for index at ci equals I. Then we can place it here. All right, cool. So now this earliest reachable, now we can solve this. So now for int start, or for int mask equals 1, mask is less than 2 to the k, mask plus plus. And then at the end, we want to return earliest reachable at 2 to the k minus 1. turn this is less than less than or equal to n. Okay. So now how do we calculate this? We want to go through all of the things it came from. So int last placed, I guess for int last equals 0, last is less than k, last plus plus. If mask and 2 to the last, if this is equal to 0, then continue. Otherwise, int previous equals mask and not last. So now we have the mask it came from. Okay, so int from end will be earliest reachable at from. Okay, so now int now start will be from, or will be next place for index at well, I guess we should say earliest reachable at mask equals n plus 1. So that way it's always possible. So now if from end is greater than n, greater than or equal to n, then we continue because we can't actually start here. Yeah. So otherwise, we need to look at where we came from and then find the next place we can start and then update this DP position. So int my start will be next place for index at last. So at this index, and then the starting position is from end. So now earliest reachable equals math.min, earliest reachable at mask, math.min of earliest reachable at mask. Or what else? So if we can't do this, we want my start plus required jump. That's the earliest time the next one could start. I'm pretty sure that's it. So let's run samples and see what we need to debug. Oh. Yeah, okay, so I guess we need if I plus required jump is less than or equal to n and this stuff. Zero, that's not great. Okay. So we need a bit more space here. So let's say, how good are these samples? This is 2, that's nice. Yeah, okay. So sys out, solving for required jump of plus required jump. Okay, now we need more space here. So for a required jump of 5, that's too big. Yeah, required jump of 2 is fine. So what are we looking at? For index I equals 9, 0, 4, 5, 6, 7, 8, 9. 9 is 11 for both of them. Okay, what about 8? For B, should be 8. Yes, this looks fine. So this looks like it's right. What about for 4? So for 4, it's 5. Yeah, okay. So this looks fine. So the next place for index is fine. Let's see if this part is working at all. So let's look at when it's 2. Okay, required jump of 2. So earliest reachable for mask 1 is 11. Why is that? Oh, yeah, this should be mask minus 1 to the last. Yeah. So okay, we get that right. That's 4. This is 2. And 0. Looks good. 3. And then 1. Looks good. All right, let's submit E. Nice, nice. All right, Rainbow's got F. Good job to him. How's our camera working? We're still... All right, still alive. Oh. Nice, nice. Okay. Let's look at D then. Excellent arrays. Okay, call an integer array good. Yeah, okay, so we have this. So we need to know... Oh, look at this. Okay. I missed this part. Yeah, there are some nice constraints there. So L is always less than 1. R is always more than 10 to the 9. So the maximum number of pairs is pretty easy, right? It's just n over 2 floored. Yes. Yeah, the maximum number of pairs is n over 2 floored. So the question, to be or not to be, question is, how many ways are there of getting n over 2 excellent arrays? What do we need to do in order to do that? So it's not the pairings that we need to count, because there are multiple ways of pairing things together. we've got like n over 2 differences, but again, it's not the differences that are important. The answer is going to be a lot. It's going to be, there are a lot of ways of doing this. Wait, hold on, what's the question? So f is the number of pairs. Oh, we want to maximize the number of pairs. So it's not the number of things in a pair, it's the number of total pairs. Yeah, like you make half of them the value plus 1, half of them the value minus 1. Is that it? Is that what we're looking for? I think that would probably do it. Yeah, you could also do their value plus 2 and their value minus 2. You could do their value plus 3 minus 3. So there's a lot you can do there. That depends on L and R. And there's also the number of things which can go in one direction and the number of things which can go in the other. And there's some things which can only go in one direction, right? Some things might be able to be its index minus 3, but wouldn't be able to be its index plus 3 because that would be bigger than R. So we can't have that. Lots of stuff. Okay. So the maximum number. So we can always do 1, 2, 3, 4, 5, 6, right? We can always do 2, 3, 2, 3, 4, and then 3, 4, 5. This will be 3 times 3, this will be 9. There's no way of doing better. If you can't be, if it's a derangement. Yeah, there's no way of doing a better derangement. So this is 3 times 3, so that's the best you're gonna get. Yeah, okay. I think that's also true for even values too. Is it true when n is really small? It is true when n is 2. What about when n is 3? Yeah, because these two need to match. Right, you need some pair that matches. The third one needs to be one of the two. Oh, but when n is odd, it's a bit tricky because the last one can be in either pair. So maybe we'll handle the odd case in a minute. Okay, so we pick like a plus x and then a minus x. So either, so like there are like A things that can be plus only, B things are minus only, and then C things can be either. What if something can be neither of those? Something can be neither plus nor minus. That's a problem. Yeah, okay, so if anything can be neither, then it's impossible. Okay, otherwise we need to choose n over 2 things. It's easier if we say this like A forced. B unpickable. Yeah, okay. Choose n over 2 things of the total. So we have n minus a minus b. Oh yeah, n minus a minus b. Choose n over 2 minus a of them. Yeah. Okay, so that's the math for that part. So we're going to need n choose k. I think that's it, right? Oops, we don't want to copy D. We want to copy our template. Yeah, what else? So we also need, so we're going to brute force what this offset is. There are a bunch of interesting offsets, and there are a bunch of offsets that anything can be. Okay, so what about the odd cases? Is it always the same as just adding one more bigger number? Probably not, no. Okay. So yeah, I guess we'll just make that a bit separate here. So we'll have some pre-comp method. Okay. So static final long mod equals 10 to the 9th plus 7. Static long add, long A, long B. And static long multiply, long A, long B. Return A times B, mod, and then we need fast pow. Need mod inverse. That's the base to the mod minus 2. Okay. It's x to the mod minus 2. Gotcha. And then pre-comp. So we need our factorials. So we need some factorial array. And then factorial inverse. All right, so fax at 0 equals 1. for int I equals 1, I is less than facts.length, I plus plus. Facts at I equals multiply facts at I minus 1 by I. Facts inverse at I equals the inverse of facts at I. And then, oh, we also need n choose k. Static long n choose k. Int n int k. So if k is less than 0 or k is greater than n, return, there are 0 ways of doing that. Otherwise, return mul facts at n divided by fact inverses at k divided by fact inverses at n minus k. All right. So now we need to read in the input. N, L, N, L and R, yeah. Okay. So what is the first time things are interesting? So I guess we'll say if n mod 2 equals 0, then we'll do this part, otherwise we'll do this other part. If n is even, yeah, okay. Let's do some math here. So yeah, I guess this is where we go back to actually solving the problem. This many forced things, this many unpickable, and this many either. So forced positive, long, forced negative, long either. These are all ints. So this is return n choose k. I guess int n equals the sum of these things. Forced positive plus forced negative plus either. So n is n minus forced positive minus forced negative, and then k is n over 2 minus forced positive. Yeah, okay. So that's the number of ways of doing that. So we need to brute force this. So we can speed this up because we know a bunch are the same. So we've got like the same answer a bunch of times, and then we have a different answer. But the times the answer is different is not that many. Like this is only 2 times 10 to the 5th. So we can calculate each of those. We just have to do this super quick. Yeah. So the offset is never 0. So I guess let's just do it naively first. So 4 in offset equals 1. Offset is less than, well, I guess true, offset plus plus. So int forced positive. This is going to be math.max of 0, and let's say L is -2. So then it would be L plus offset. Yeah. Forced negative equals math.max of 0. Offset minus r minus n, I think. This might not be right exactly, so the biggest thing is r. Yeah, these are indexed by 1, right? 1 indexed? Yeah. So the biggest index is n. Yeah, so this is forced negative. Okay. If forced negative plus forced positive is greater than n, then break. Okay, otherwise we have our answer, right? So we have long ans equals 0. And then ants equals add ants ways with forced positive. So if either is less than 0, that's just easier to understand for me. So forced positive, forced negative, either. Ants equals that. And then we're good. Yeah, so this should work in cases when n is even. So it should work in this case. We should get 10. Print answer. Zero. Why is that? So 4 things are either. Why are we adding 0? Force positive, force negative, either. So n equals 4. So this is 4 minus 0. Choose 4/2. What is my n choose? Because I don't call pre-comp. Is my pre-comp wrong? Facts at I equals multiply. Oh, facts is inverse of facts at I. Yeah, that's right. Fact ins at 0 equals 1. Maybe I'm missing that. Okay. Exponent equals 0, return 1. Oh, this is base. Yeah, that's right. Okay. Now we get 10. Looks good. All right, so we have a long way to go still, but we're making progress. We have our basic math working. All right, so now the question is, we have to make this faster. How do we do odd cases? So we have the offset. There are 2 ways of doing this. So yeah, so we might need to choose the smaller half, or we might need to choose the bigger half. So if n mod 2 equals 0, then it's this. Otherwise, yeah, there are 2 ways to do this. So int k1 equals n over 2, and k2 equals n over 2 plus 1. So long ants equals 0, ants plus equals n choose k. So our n is n minus forced positive minus forced negative. And then we choose k1 minus forced positive. And then ants equals add ants and choose k. So n is n minus forced positive minus forced negative, and then we choose k2 minus forced positive, I think. Then return ants. So I think this should be the same. So now we should get all of the cases right. But just be too slow. 210 something, 1463, but we get this wrong. Huh, okay, why is that? Because there can be one thing. Yeah. This is crazy. Okay. Yeah, there can be one. There can be one time where this isn't the case. So in this case, either can be -1. So if either is less than -1, then it's impossible. Oh, really? I thought that was it. So when does this happen? This happens, I guess, n is 3. And then the offsets, well, you can have like 5. Yeah, you can have 4. Okay. N is 3. L equals -1. R equals 4. Oh, okay. So this math is different in this case. So for even numbers, everything gets picked. For odd numbers, there's one thing that doesn't get picked and can be any value. No, it can't be any value. It's got to be one of the two values. It's got to be +1 or -1. Yeah. Yeah. So this should be 0, actually. I guess it would be helpful to have a brute forcer for this. How much time do we have? Yeah, it would be nice to have a brute forcer. So I'll write a brute forcer real quick. This is the outer loop. Okay, then check. Yeah. Okay. So this will check everything, check all arrays. So how do we check an array? So there's our brute forcer. All right. So let's try this. I got this case right. Yeah, okay. Arrays dot fill A with L. Five, what? 4 over 2 is 2 times O. Okay. All right. So minus 1. There we go. Brute force, so the answer to this should be 4. What do we print? 4, okay. If we make this minus 2. The answer is still 4. What if we make this 4? Then it's 10, okay. Okay, we get the 10. What if it's 5 and this is 5? 50. 15. Okay, what about 505? 39, so we'll almost certainly get this wrong. Eight. We're getting n right. So we choose which ones to be positive and which ones to be negative. What if we just print the array here? Oh. Yeah. We have to, I guess, watch out for the case when anything equals itself. So for int I equals 0, less than a.length, I++. If a at I is equal to I plus 1, then continue. Oh, then return false. Okay, so the answer is 14. Which is not what I expected, but okay. So minus 3, minus 3, minus 3, plus 3. So plus 1, minus 1, minus 1, minus 1, plus 1. So minus 1, plus 1, plus 1, plus 1, minus 1. So is the answer 14? We say 8. All right, let's say what the offset is. Max offset's equal to 1, and max pairs equals n pairs, then 0 offset count plus plus. This is actually the 1 offset count. And then this out 1 offset count. So they're 10 with the 1 offset. Okay, that's kind of wacky. So why is that? So there are 10 ways to do it with an offset of 1. So if 5 choose 2. Okay, so you have one thing that's forced positive, one thing that's forced negative, 3 choosable. So you can do plus. Oh wait, do you have anything that's forced negative? You have nothing forced positive. Yeah, because it's 0 and 5. 1 forced negative, 4 choosable. So you can do plus, minus, minus. So this one is forced minus. The last one's forced minus. So you've got, so there are 4 ways of doing this. And then you can have 3 minuses. You can have plus, minus, minus with the last one forced minus. Then you have 4 choose 2 ways of doing that. How many ways are there? So there's 1, 2, 3, 4, 5, 6, 7. What is 4 choose 2? 1, 2, 3, 4, 5, 6. Yes, there's 6 ways of doing that. Okay. So let's debug this then. We need 5 over 2 is 2. 5 over 2 plus 1 is 3. That's right. So n, so this is 4. Yeah. 4, choose 2 minus 4 is positive. So there's one forced positive, one forced negative. Why is that the case? Forced positive equals whichever is bigger, 0 or L plus offset. So the L is 0, the offset's a 1. This should be minus 1. This should probably also be minus 1. $14. Is that the right answer? $14. Okay. All right, so then we should pass all of these, hopefully. Six, 9, 4, 4. Okay, good. Yeah. Looks good. Okay, so now we have one part of this problem left, which is how do we skip all the parts that don't matter? Yeah, so when will this start mattering? Is it true there are not that many things that matter? So I guess we could binary search the first time it matters. That would work, I guess. So we just need we need these two things. We need this to be the case. So yeah, so we want L plus offset minus 1 is greater than 0. So what does that mean offset is? So that means offset is greater than 1 minus L. Okay. Yeah. And or we want offset minus r minus n is greater than 0, which means offset is greater than r minus n. Yeah, okay. Okay, so yeah, let's copy this in case we break it. So then long times will be, okay, so I guess this is like the number we can skip. So this will be math.min, whichever is smaller, 1 minus L, or R minus N. Okay, so we do, yeah. So if n skip is greater than 0, then we actually add it. We should be able to add it here. This is the same code either way, I think. Yeah, I'm pretty sure this is the same thing for both cases, so we will ignore this part. And then just make this fast. Okay. That's what we're doing. So if n skip is greater than, yeah, greater than 0 should be fine. If it's at least 1. So 1 plus n skip, that's where we start counting, okay. So long multiply, or like times effective, this will be n skip minus 1, and then ants equals add ants. So ways with 0, 0, and then there are n that can be either. And then we want to multiply this by times effective. Yeah, I think that's it. It's not it. Very much not it. Okay. Okay, so what are they saying here? So when n equals 1, nothing is forced. Then when n equals, the offset's 2, we start going. What if we just do this? Then we should have the same answers as before. Okay. So something is wrong here. This is not equivalent for some reason. So forced positive would be, oh, minus 1. Yeah. L plus offset minus 1. This is greater than 0. So offset is greater than 1 minus L. So n skip is 1. So 0, 0, 4. Oh, I see why. Should be, yeah, just that. Okay. All right, submit D. Took way too long, but we got it, I think. We'll see. Nice. All right. There's my contest. How's Rainbow doing? Nice job, Rainbow. Well done, sir. Well done. You got all the hard ones. Rainbow is actually quite good. Very impressive. Let's get Buffoon going for the Rainbow strat. Uh-oh. I wonder if this was a legit submit or not. Very curious. Alright. So, what is F? I guess we'll read it real quick and then probably do solutions. What do you say? Is our camera still going? There we go. Camera's still on. A little foggy. Hello. This is me. Alright, cool. There is an infinite pond that can be represented with a number line with n rocks on the pond, numbered 1 to n. The ith rock is located at an integer coordinate ai. The coordinates of the rocks are pairwise distinct. The rocks are numbered in increasing order of the coordinates. So a1 is less than a2 is less than an. Gotcha. So you have a bunch of rocks with coordinates in order. A robot frog sits on a rock number S. The frog is programmable and has a base jumping distance parameter D. There's also a setting for the jumping distance range. If the jumping distance range is set to some integer k, the frog can jump d minus k to d plus k. Okay, makes sense? The distance between two rocks is the absolute difference in their coordinates. Awesome. So we're assigned a task to implement a feature for the frog. Given two integers, I and k, determine if the frog can reach rock number I from a rock number S, performing a sequence of jumps with the jumping distance set to k. The sequence can be arbitrarily long or empty. We will be given q test cases for this feature. The jth test case consists of two integers I and k. Print yes if the ith rock is reachable, and no otherwise. Is S, what is S? Oh, some starting rock. So you have a bunch of, yeah, so you've got a base jumping distance, and then you have a bunch of rocks. And then the question is like, for some range k, can you reach some other rock? Can you reach some rock? So there are some rocks you can reach with the jumping distance of 0. And then there's some, or with like k equals 0. And then as k increases, there are more and more rocks you can reach. So yeah, you've got like you kind of want a minimum spanning tree, right? You want to make the minimum spanning tree here. And then you want to query the min along a path on the tree. Sounds to be the right answer. So the question is, how do you make this minimum spanning tree efficiently? And are there more than n edges you need to consider? Yeah, probably not. I think there are 4 n edges in the graph. Oh, not quite. That's not quite true. This might be Baruvka's algorithm. Yeah. Geeks for geeks. I don't know. I just feel like overwhelmingly they do a terrible job explaining stuff and their code is terrible. The third MST algorithm, how does it work? Okay. Yep, no one cares. Goodbye. Let's look at this Columbia PDF maybe. So Baruvka, pick a node, or every node picks its minimum incoming edge, adds that to the spanning tree. Then you contract all edges in T. Yeah, so you do Baruvka's. So that's the idea for D. All right, or for E, for F, I mean, sorry, what am I saying? Okay, let's do solutions to all of the problems. What do you say? Okay, let me get my drawing thing here real quick. All right, good morning. I hope you had a great contest. I had a pretty fun contest. I enjoyed solving and thinking about all the problems. I didn't solve all the problems, but I enjoyed thinking about the problems that I solved. And I think I have a solution idea for F. So we'll talk about all the solutions here real quick. Oops. How do I scroll? There we go. Okay, so here we go, solution time. So for problem A, so for problem A, the first thing to notice what the problem is you want to make some array which is beautiful by their definition of beautiful, where the sum of elements is equal to S. And you can make an array that's beautiful with the sum of elements equal to S for any S by just having a bunch of ones up until the sum equals S. For any positive S, at least. So it's always possible. The question is, what's the minimum number of elements you need in order to do this? And their definition of beautiful is either like the array has to contain a 1, but in addition to containing a 1, every element that it has, you have no jump between elements that are like adjacent in value by more than 2. Right, so you can't have a 3 and then your next biggest element is a 6 because that's a jump in value by 3. So the elements have to be, if you sort them by value, they have to be basically increasing by 1 or by 2 at each step. So what we can notice here is if we look at the best way of doing this, the array we get looks like this. It's 1, 3, like if we make the biggest jumps possible, 5, 7, and then 9. And then maybe in order to hit the target sum, right, since we have to hit the target sum exactly, maybe the next number we need is like a 6. Well, if the next number we need fits anywhere in here, it will be an okay number to place, right? Because we're allowed to place a 1 if we want, or we're allowed to place any number that differs by 1 or by 2 here. So if we have a 6, then that's fine because you have this 5 minus 6, which is 1, and then you have the 7 minus 6, which is also 1, right? So what we do is we just, at each step, we place the biggest number we can, and then once we have just some left, we'll just place that. That's how you actually construct it. In order to solve the problem, you don't actually need to construct the array. You just need to say how many steps will it take. So it's even easier than that. You just write like a for loop, right? So what the actual code looks like, very easy. You have your sum, you have an integer for how many things you've placed, and then what the next thing you're going to place is. You place the biggest thing you can, you increment your count, and then the next thing you place is 2 more. And then once you've overshot your total, then you print 0. or overshot, or your total is equal to 0. Then you're done. All right, yeah, so that's the solution to problem A. Pretty easy. Seem to have lots of solves in contest too. For problem B, maximum deletion, the problem is you have some continuous subarray, and you can delete, or sorry, you have some string, a binary string of 0s and 1s. Maybe it looks like this. You can delete a continuous range of the same character of all 1s maybe, or all 0s, for the cost A times the length of this substring plus B. A and B can be negative, and you want to know what is the maximum possible cost of deleting the entire string. Is it maximum or minimum? Yeah, the maximum cost of deleting the entire string. And yeah, there are different ways of doing it, right? Because you have choices on how wide these ranges that you delete are. So it's not just like a fixed thing. Importantly, you don't have to delete a maximal substring. You can delete something that isn't maximal. So, okay, how do you do this? Yeah, a couple observations. The first one is that this A part is not very important or difficult to handle. You know every character is going to get deleted, so the total sum of lengths will be the total length of the string, right? So this A times L part, at the end, that's just going to be N times L. So all that really matters is how many times are you adding B. And either if B is positive, you want to add B as many times as possible, or if it's negative, you want to add it as few times as possible, because you want to incur the penalty as little as possible. So let's say you want to add it as many times as possible. Well, if that's the case, just delete the characters one by one, right? Every single character will be the same as itself, so you can do that. If B is possible, that's easy. So if B is positive, then the answer is just going to be A plus B times L, right? Because the total sum of lengths will be L, and then the number of segments you have will be L, because you want each segment to be separate. The other case is what happens if B is negative. Well, in that case, you want as few groups as possible. So to get as few groups as possible, what you want to do is either delete all of the groups of 1s, and then after that, you'll have all the 0s left over. You delete all the 0s. Or you can do the opposite. You can delete all the 0s. At the end, you'll have all the 1s left over. You delete all of them. So either this is the min of the number of groups of 1s, the number of groups of 0s, whichever one of these is smaller, plus 1, this part times B. That's how many deletions you're going to need, assuming B is negative. And then you also want plus A times L. And that's the solution. There you go. All right. So yeah, that's the idea for A and B. I'll show you the code for B real quick if you're interested. Looks like this. Yeah. So that's the idea for B. Awesome. Let's move on to problem C real quick. Manhattan subarrays. So yeah, for this problem, they define a Manhattan triple, or like a bad triple. If you look at them in Manhattan distance, their middle point is in the middle of the two, I guess. So a bad triple would look like this. I'll draw these on like the XY plane here. Because if you do Manhattan distance, the distance to these here, this distance here, is equal to this distance plus this distance. Because you can imagine moving this segment down. So you have this, and then this segment over. So now you have this. Right? So they're really the same. An example of something that isn't a bad triple would look like this. Right, so the Manhattan distance here plus here, that is going to be longer than the Manhattan distance here, because we double count this part here. So in other words, the Manhattan distance is equal if it's like an increase of the 3 or a decrease in 3. That's when it's a bad triple. So you want to see, let me make sure I say this correctly. You want to see how many subarrays, how many contiguous subarrays have no bad triples in them? So yeah, let's look at what that would be. So you have some big array of size 10 to the 5th. You want to see how many subarrays of that array have no bad triples. Well, here's the thing to notice. It's possible to have 4 elements that have no bad triple. You can have elements that look like this. Right, so if you pick any 2, like this one and this one, you're not going to be able to pick a third one to its right that's bigger than the second one or smaller than the, like if these 2 are increasing, that means anything to the right of this will be smaller than it. So yeah, so in this case, these 4 elements have no bad triple. But one thing you'll notice is if you have a 5th element, no matter where you place it, right? Let's say you place it here, down here, then you have a bad triple, which is this one, and this one. Because these are that you move right, as you move right, they decrease. So yeah, it's impossible to have 5 elements that don't have a bad triple. There's some proof that I talked about with Ericto, but basically, if you look at the longest increasing subsequence and then the longest decreasing subsequence, one of these have to be at least the square root, right? So they can't both be smaller than the square root of 5. Otherwise, you have self-contradictions. So yeah, so that's the idea behind this problem. Anytime the subarray is 5, you can skip it. You can ignore it. So you just have to check manually all subarrays of length 3 and 4 because they might work or might not. And you know all subarrays of length 1 and 2 will work. So yeah, that's the idea. The code is pretty simple. We just brute force the left endpoint of this range, and then we brute force the right endpoint. If it's 5 or more, then we break. We can skip this because we know they're not going to work for anything any longer. If it's less than 2, we count it. Otherwise, we manually check if there are any pair of 3 that would be a bad triple. So the 3 increase as they go right or decrease as they go right. Yeah, all right. That is problem C. Hopefully that made some sense. All right, problem D, excellent arrays. Yeah, so for this problem, you're looking for these things that are derangements. It's a permutation where the value at every index is different from what the index is. So the value at index 3 can't be a 3. It has to be a 4 or a 5 or a 1 or a 2, but it can't be a 3. So yeah, that's what you're looking for. You want to find derangements, but they have to be derangements with an additional constraint, which is you want to maximize the number of pairs where the sum of the indices is equal to the sum of the values. So let's give an example here so this makes a bit more sense. If we have the array 2, 3, 1, 2, 3, 2, 3, 4, the indices, I'll write them above, is 1, 2, 3, 4, 5. So if we look at these 2 pairs, this pair here and this pair here, the first thing you'll notice is the value of every index is different from its value in the array, right? There are no things where the 2 numbers match. So this means it's a derangement, so it's okay in that respect. We also want to look at the number of pairs where the sum of the red numbers is equal to the sum of the white numbers. So both, in this case, they both equal 6. There are a bunch of cases in which this is true. In fact, in this array, there are 6 pairs. So if you look at these 2 circled in blue, in this case, the difference between them is going to be positive 1. And then for all the 3 circled in green, the difference between these is negative 1. So any blue paired with any green, that will make some total where the red numbers are equal to the white numbers. The maximum is obviously 6, right? So you want to make the blue and the green about equal, and then the number of blue columns times the number of green columns, that'll be maximal if they're equal. Because if you have numbers that have the same sum, you want the two numbers to be as close as possible for their product to be as big as possible. That's just kind of like a greedy principle for how multiplication works. I don't really have a proof for that, but I'm sure proofs exist. So yeah, that's the general idea. And one thing to notice here is like the absolute value of all of these differences are the same. That's the key principle. And that's the case because if we like split these up, then we would end up losing pairs that work together, right? So yeah, okay. So this is what we're looking for. We want to maximize the value of this 6 here. And this is obviously the best way of doing it. So you make the first half of your numbers one more than their index, and the last half of the numbers one less than the index. Now that would be a pretty easy problem if that were it. What the problem is actually asking is, among all arrays, where all elements in the array are between L and R, how many arrays have this maximum value for the number of pairs you can add up, where the sum of the white numbers is equal to the sum of the red? An important constraint here, which I missed the first time I read it, is that L is always less than 1 and R is always bigger than N, which makes the problem much easier. So you already know what the maximum number of pairs is. I kind of already told you. It's n over 2 floored times n over 2 ceilinged. So basically you're answering a slightly different question, which is how many arrays with these constraints can make that number of pairs of perfect things. So yeah, that's the idea. Okay, so how do we solve this? So what we're going to do is we're going to brute force what this value is. So what the absolute value of this difference is. When we know the absolute value of this difference, we know, okay, there are some indices which are forced positives, right? So there are some prefix, right? Let's do a different example here. So I'm going to write out the indices in red again. So let's say the indices are 1, 2, 3, 4, 5, 6, maybe. So, and let's say the value that we're considering is going to be 2. So if the smallest thing that's allowed is 0, and the biggest thing that's allowed is, let's say that's 6. So this 1, we have to do positive 1. The thing that matches the 1, it has to be a 3, right? It can't be a negative 1 minus 2, because that would be less than L, which is 0. So we know this is going to be a 3, so we know this is forced to be positive. What about the 2? Well, the 2 could be 0. It could be 0 or 2. Or 0 or 4, sorry. So this can be either. This has a free choice. The 3 has a free choice as well. The 4 has a free choice, right? This can be 2 or it can be 6. The 5, it has to be negative. So the 5 has to be 3, and the 6 has to be 4, because they both have to be less than R. So the question here is, we want there to be 3 elements that are chosen to be positive, and we want there to be 3 elements that are chosen to be negative. We have 1 element that's forced positive and 2 elements that are forced negative. So the question is, how many ways are there of doing this? We want to answer that question ideally in order 1, so as quickly as possible. So yeah, how do you do this? So we can do it with some n choose k, right? So in this case, we have 3 empty spots, and of the remaining ones, we want 2 of them to be positives. So 3 choose 2, that's equal to 3. There are 3 ways of doing this. Alternatively, you could do 3 choose 1, right? So we have to assign 1 negative to these 3 in order for the sum to work out. So yeah, that's the general idea. So basically, to summarize, we brute force what this difference is. In this case, the difference was 2. We would try a difference of 1, a difference of 2, a difference of 3, a difference of 4, and we'd keep going until we decided, oh wait, this doesn't actually work anymore. And then we know what the difference is. So we know which things are forced to be positive, forced to be negative, or can be either positive or negative. And with that information, we can do n choose k math, combinatorics, in order to say how many ways are there for there to be this absolute difference. So that works. The problem is it's a little bit slow. So you have to do math and notice that in the beginning, all of the answers are the same. And then they're all the same up until the last like 2 times 10 to the 5th answers. So you can do just multiplication to speed up that transition so that your runtime winds up being order n rather than order 10 to the 9. It's a little bit messy and annoying, to be honest. So I'll just kind of talk about what that math looks like here. So the n choose k, yeah, I ended up writing a brute forcer for this because it was annoying. So let's get rid of the old commented code because we don't need this. Yeah, so the n choose k part is pretty easy. Oh, I guess there's one thing I didn't cover, which is if n is odd, there are 2 ways of doing it. You can either have, like, let's say n is 5, you can have 3 positives and 2 negatives, or vice versa, right? Or 3 of one, 2 of the other. So yeah, so you have to consider both possibilities. Those are both allowed. Anyway, how do you actually do this? So for n choose k, you know how many are forced positive, how many are forced negative, how many are either. The total number of unchosen things you have are the ones that are, I guess this is just either, right? This is equivalent to just either, the ones that can be either of them. You need n over 2 things to be positive in total, and this many of them are forced. So you can ignore all of those. And then you do the same thing for odd. You just try both possibilities and then add them together. For n choose k stuff, this is just factorials and mod inverse. So yeah, there's that. If you're new to mod inverse, I made a video on it. It's an earlier algorithms thread video, so check that out if you're very confused on why I'm taking stuff to the power of mod minus 2. Yeah, this is a bit confusing if you're not familiar with it. Okay, and the last part to talk about here is figuring out how to skip stuff in the beginning. So we have these 2 equations for when these things start being effective, right? These 2 equations right here. And initially, for a lot of offsets, they don't matter at all, right? The 0 is just chosen for everything. So for the first whole bunch of times this for loop runs, the 0 is what's important for both of these. And for each of those times, we can just process this really quickly and then multiply the answer by the number of times this will happen. So yeah, that's what we do. And we just calculate the number of times it happens with some math, which is a little boring. So I won't spend too much time talking about it because, yeah, we don't want everybody to fall asleep on me. All right, almost done here. Problem E and problem F I want to talk about. So yeah, problem E is pretty straightforward. It's a common idea. They kind of give away the solution by the fact that k is 17. That should be pretty obvious. If k is 17, it kind of screams a 2 to the k solution. So that's what I went with. And in order to get 2 to the k to work, you can't have n in your state. So the only other place that n could be is in the transition, or like in the result of the dp. And in this case, it's an inverse state dp. So I guess I just told you the solution. What's the problem? You want there to be, you have some answer, right? Let's say the answer is I don't know. So, okay, let's not do that. You want to maximize the longest continuous run of the letter where the longest continuous run of that letter is the shortest, right? So you want to maximize the longest continuous run of every letter. The one that counts is the shortest longest continuous run of that A. So let's say A has the longest continuous run of 10 and B has the longest continuous run of 3. Then your score would be 3. You want to maximize that 3. The question is, if you try and maximize that 3, how big can you get it? So maybe you get it to 5. So obviously you can binary search what that value is. So we binary search what the thing we're trying to maximize is. After binary searching that, we check, can we do it? And we do that using a 2 to the n dp. So the dp stores if we've covered this mask of letters, what is the shortest prefix we can use to cover that mask of letters? Or is it impossible to cover that mask of letters? And then the transition is for each of the next possible letters, we'll try covering it. So yeah, that's the idea. It's that easy. The code for it is pretty quick. So we're going to do a binary search for the answer. Then we need to check whether this answer works or not. So we'll make a prefix sum for each character where the question mark counts as that character for each character. So we do that, we have the prefix sum for each character. So now we can check, is this range of characters, is this all things that might be a C, for instance? So then we say, if we're looking at this position, we start at this position, when is the next time we could place 7 C's in a row, right? When's the next time we can place the required jump C's in a row? And we can do this just by doing a sweep from the end to the beginning. So we say, can you place a C here? If you can, then do this, and you can check if you can place a C here in order 1 using this prefix sum array. So use the prefix sum array to check if you can place a C here. If you can, you do. This is the earliest you can place it. Otherwise, it's the earliest place you can place it, starting at the next position. And then finally, we do this 2 to the n dp part. So we brute force what the last thing we place is. This is like the last character that you end up placing. And then before this, you know, okay, what was the mask without this last character? So you know the mask without the last character, and then you know the last character you place. You've previously calculated the DP for stuff without the last character. And now we're saying, okay, so now we're going to place the letter F. And we know we had to use the first 20 characters of the string to place the other letters in this mask that we're interested. Maybe we placed A and C. It took us 20 characters to place our A's and C's. Now we need to place the character F. So we start at index 21. This all has to be, we have to place like 7 F's maybe. So we're going to use this next place for index to see, okay, where's the next place we'd place it? And then we know the answer for this value, or we know the answer for F's would be, we know where we can start placing it, and then we place 7 in a row, and that's the end place for F. So that would be the answer for this DP value. Then finally, the answer we return is, well, it's possible if you can place all of the characters using at most the entire string, right? So can we place all of the characters? It doesn't matter what order we place them in. We just have to be able to place all of them, and we'll try all of the orders in the DP. But we have to be able to place all of them, and the number of characters we have is at most n. So that's the idea. This is left shift, which is obviously like 1 left shift k is in binary. If you have a 1 followed by k zeros, that's just 2 to the k. So that's what that means. But yeah, this is some bit operators. I think it's a good problem, especially for an educational round. It teaches you a lot. All right, and then finally, I'll talk about what I think the solution to F is. I didn't have time to solve it, but I'm pretty sure I have the right solution. So you have n rocks, and you have a bunch of queries, which is for some, you've got some distance that you jump by default, and then you have like a variability in that jump distance, which is k. So you can jump to like your position plus d plus or minus k. Those are the range of positions your frog can jump to. Now, the question is, you've got a bunch of queries, which are, if you start at this position, can you reach this position, this other rock, with a jumping distance of, or with a jumping range of k? So the way the problem is built, you start at some position. There are a bunch of rocks you can reach with position 0. After that, there are a bunch of rocks you can reach with, so not with position 0, with like a variance 0. So if k is 0, there are a bunch of rocks you can reach. All of those will be a multiple of d away, right? You just keep jumping d left or right, and then you'll hit a bunch of rocks. Now, if you increase k to 1, there will be more rocks you can reach, and if you increase k to 2, there will be more rocks you can reach. All you care about is the minimum k required for you to reach each rock. And the structure that handles that perfectly is a minimum spanning tree. So what we want to do is calculate the minimum spanning tree, and then we want to do some range queries on this minimum spanning tree in order to effectively calculate what is the k required to get from one point to another. Okay. Yeah, I have to go soon. But yeah, so that's what we're looking at. And then the only part of the problem that's left is how do you calculate the minimum spanning tree. You can use this algorithm called Beruvkas, and it works out really well in this problem. But what Beruvkas is repeatedly what we'll do is for every node, we'll find the closest node to it, the node that would require increasing k the smallest amount. And then you connect those two nodes and then join them up in the tree. So yeah, you can repeatedly do this. I'm pretty sure that you can do this using a priority queue for each section. But like I don't have the details for how to build the MST totally figured out, but I'm pretty sure this is the way to go. So basically what you can do is for each node, you have like a pointer to the left and to the right of the nodes. Like if you imagine if you jump to D, you look at the first node after that and the first node before that. And then you see like, okay, there's one of those you can reach possibly with this many steps. You look at whatever the minimum edge in the spanning tree is that you would add. And that is, why am I looking from D? Look at the minimum edge you would add. That's what you add in this level of Beruvkas. You can prove that Beruvka will finish in at most log n iterations because the size of each component after k iterations is at least 2 to the k, right? Because after the first iteration, everything is size 2 because you join all the things together. After the second iteration, everything's at least size 4 because you've joined 2 nodes of size 2 together. So yeah, so it'll combine pretty quick. Yeah, and you just have to be able to maintain what is the closest edge to this component quickly. All right. So yeah, that's the solution to all of the problems in the educational round. If you didn't like my solution to F, or it was a little hand wavy, the editorial will be out in 12 hours. But until then, I guess that's what I got. So thank you for watching. Hope you had a great contest and hope you enjoyed the problems as much as I did. All right, goodbye.